Hey, what's up guys? So this is going to be a first of many videos in which I discuss a new project I just started working on in making my home smart. And what I mean by smart is I'm basically creating a wireless mesh network of sensor nodes here in my house that are all communicated with via a single main host station. So the first step of this project was to establish the wireless communication. And for this, I chose to use the NRF24L01, which is a great wireless transceiver. It operates at 2.4 gigahertz. It's got plenty of bandwidth to do this sort of thing. And the best part is it's really cheap. So if you want to add wireless communication to your Arduino project, that's basically what this entire video is going to be about. And I'm not talking about using any pre-written libraries or anything like that. We're going to just go right through the code and how to talk to this via a standard Arduino Uno. So let me show you what I'm talking about here. Okay, so what we have here is two Arduinos, both with a NRF24L01 Plus attached. This is really cool code that I've got running here, and it may not look like it's really that cool until I explain what's happening here, but basically, on this Arduino, we have a push button connected and an LED connected to standard digital pins on the Arduino. And if I push this button in, the LED blinks. So, I mean, that would probably take just a few lines of code on this Arduino to make that happen. But what's interesting of what we have here is that there is no code running in this loop at all on this Arduino. Everything is actually controlled by this Arduino. So in this Arduino's loop, we're monitoring this digital input. And if we ever see this pin go low, because we have the pull-ups enabled on this, it will then turn or flash this LED over here. So that's all controlled by this Arduino. This Arduino is handling everything. It's grabbing the status of this pin and it's driving that LED pin high and low. So what we basically have here is transparent control over this Arduino's I/O. So we can control all the pins we want from this. We can even set up the pin modes over here. So basically what I'm getting at here is that you set all of your sensor nodes up with the same code, and then this host Arduino will go out and configure all of the I/O that you want for the sensor. So, you know, I'm configuring the push button pin as a digital input. I'm configuring the LED pin as an output. So it's all handled by the host. So it's really cool stuff, and we'll get into all the code and how it all works in a second. But even cooler, by the way, is that these two guys are both running the same exact code. The only difference is that this guy here has nothing in its loop. No code running in the loop. So this one could actually control this one. So they could almost control each other if you wanted to. But anyway, let's just talk a little bit about the hardware here. So this is the NRF24L01 Plus module. So you can buy them with these modules, which is great, and they're really cheap. So they come with a 2x4 header, which really kind of stinks because you can't use that in any breadboard. It doesn't really plug in anywhere on the Arduino, so you need to either buy a breakout board for it, or you need to just remove the header and solder wires onto the board itself, like what I have here, and that's exactly the way I did it. Eventually, what I'm going to do, though, is make up my own little Arduino board that basically just has an Arduino, a 3.3 volt supply, and this board. So let me leave a comment if you'd be interested in something like that, too. Maybe I'll sell them on my website or something. So basically, though, to hook this up, you can see there's nothing special needed at all. The only thing that you need is a 3.3 volt supply. This board only runs on 3.3 volt supply. So if you're running your Arduino on 5 volts, unfortunately, you need a separate regulator just for this board. So anyway, you get that. We can go right through the pins here. So your VCC and ground. VCC is 3.3 volts. Ground is ground. That's pretty easy. The nice thing about this board is all of the I/O pins on it are 5 volt tolerant, so you don't need any level shifters. So even though you're powering the board with 3.3 volts, you can still output 5 volts to the digital inputs on the board for the communications. And this will only output 3.3 volts on the output pins of the board, which is just fine for the Arduino since the Arduino's pins are 3.3 volt tolerant. So if you go right through the pins, it's pretty simple. You have your you have a chip enable, which sets it into TX-RX mode. You have a chip select pin to enable the SPI interface for the chip. You've got your MASI and MISO, master out slave in, and master in slave out. You've got an interrupt pin, which goes low when when an event takes place on the chip. The way I'm using it is when new data is present on the chip, make the interrupt pin go low. That way I can trigger an interrupt on the Arduino and then go grab the data. You also have the SPI clock. So in total you have 8 pins on that. And I think from my code it'll be pretty obvious on which pins on this are wired to which pins on the Arduino. So speaking of the code, let's jump over to that right now. Okay, so here's the code, and like I said before, we're not using any libraries, so everything is going to be written in one single Arduino file. So, feel free to copy and paste anything out of here you want to use. If you don't want to use my code at all and you just want to get a better understanding of the chip, that's fine. I don't care. I'll put everything that you see here up on my site, so check the description for a link or something like that. So anyway, let's just jump right in. So first thing here is I define the pin outs of both the transceiver and the Arduino. So you can see here that pin 1 on the NRF module is ground to ground, VCC to 3, CE to 4, CSN to 5, and I'm also showing the direction here too. So this is an output on the Arduino. So this is just kind of helpful. And basically, I wrote this code as a first draft at this point. So I'm just using the code right now as a starting point for the project. I'll eventually clean all this up and create some kind of library that's a little bit easier to use than this. But for what I've come up with so far, I think it's ready for a video. Okay, so anyway, we defined the pins. Here we got, the only thing we've got to include is the SPI library. We've got then a definition of all the pins here. A few global variables, nothing special. Jumping right into the setup here. Your serial port is going to be your best friend with this module because you're going to need some debugging. And the only way to really truly debug everything out is through the serial port. So set that up at 115.2. I'm running it at 115.2 for a reason, because the serial library and interrupts don't really go hand in hand with each other. So you might run into issues where you're doing serial.prints within an interrupt and things just freeze up. That's going to happen to you. So you need to make things happen really fast, and you got to really watch your timing. So I'll explain that a little bit more as we move through this. But anyway, all right, setting up. Then we got a subroutine here, NRF initialize. I'll drop down to that real quick here. The code's really not too bad, actually. So if we jump down here to NRF initialize, if I can find it here. Again, not really too prepared with this video, just winging it as usual. Oh, come on, where is it? It's coming up. NRF initialize, right here. Okay, so basically we're setting up all the pins, CE pins and output, CSNs and output, MASI pins and output, MISO pins and input, the clock pins and output. Then we do print. Then we've got to set up the SPI port. And the way this module works, you can actually check the datasheet here. And the datasheet you really got to rely on this and go to it a lot, especially when you're talking about working with the registers. What am I doing here? I'm just going to show you where this is at here. Okay, yeah, so this is where it shows you the SPI timing here. So you can see that when the chip select line goes low, that's when you start clocking your data in. And you can see that the clock is held low when it's not active. And if we look here, master out, slave in, you can see that new data is clocked in on the rising edge of the clock line. So you can see you have a rising edge while the data is ready to go here. Okay, so I just wanted to show you that. So that is SPI mode 0, which is rising edge of data, and that keeps the clock low. Now I'm running my SPI at 8 megahertz, so I'm just dividing it by 2, but you can really run it at anything you want. So with the Arduino, you're not going to go too fast for it. So I'm running it as fast as I can with the Arduino at a 16 megahertz clock. Dividing that by 2 to give you 8. I think a lot of people are actually dividing that by 4 when working with this module. Okay, so then what we do is we put it in RX mode right away by writing the CE pin high. And then we let it sit high. The CSN pin needs to always be high when you're not talking to the device. So it's an active low chip select. And then we kick off the SPI interface. So SPI to begin, and then the NRF is ready. All right. That was pretty easy. Then we jump into setting our first register here. So this is NRF set RX payload. So the device needs to agree with the device that's sending data as to how much data is coming along. And you've got a 32-byte pipeline. I think you have like 4 or 5 pipelines. I'm just using one pipe. So pipe 0, and I'm setting it up with 3 bytes. So let's jump down here to that, where I do that. Where is that? I'll find it here. Right here. Okay, so we have 2 things that jump into this subroutine. You've got the pipe, and then you have the bytes. So I'm just doing a 3-byte message. So everything is sent over via just 3 bytes. And you can see here what I do is I take I set up the address to equal the pipe plus 32 plus 16 plus 1. So this is the register address. And I'm just going to break this down for you real quick here to show you how this all works. So if I go over here and I look right here, you got to go down to SPI commands of the user manual. And you'll see that if you want to write to a register, which we do, you have to write a 001. So this is a value of 32. So basically, I'm just adding 32. And then the A's here are the actual address of the register. So if I go down here now to where all the registers are, right here, it's starting at 0 and it's all hexadecimal. You can see that I'm going down to 16 plus 1, so that should be a 1, 0. Here, well, it's actually 16 plus a 1 gives you 11 here in hexadecimal, 1, 1. And you'll see here that that address is RxPWP0. So this is number of bytes in RX payload in data pipe 0. So that's basically what I'm doing right here. So 16 plus 1 gives me the hexadecimal 1, 1 plus the 32 so that I'm writing to it. And then that sets up the address. So I mean, if I went pipe 1 there, you know, it would actually be this address here, this pipe. Oops. Okay. So moving along here, what it does then, now you've got the address of the register, so then it pulls the chip select line low. You pull it low. Now you're ready to talk to it. And when you talk to SPI, you actually have to, it's full duplex, like you're sending data and you're receiving data at the same time. So when you're receiving data, you're making it equal here. So data in of 0 is equal to SPI.transfer. This is actually going to send this out the pipe. This is what's coming back at the same time, okay? So you send out first your address. This is telling you that you want to write to address 17. Then the next byte you send over is the actual information you want to write to the device, which is bytes. So we're writing a 3 there to address 17. You're setting the RX payload to 3 bytes. All right, then we just do a little bit of serial printing there for debug, just so we know, that we did write it. Okay, moving along here, set the payload. And then what I do here is just for some debugging, I go and grab the status register. So this is NRF get address 7. And the way I have this set up is when you use get address, the first variable you send down is the actual address number. Then the second one could be either 0 or 1. 0 meaning that you don't want it to print to your serial monitor window. 1 meaning that you do want it to print. So in this case, yes, I do want it to print. Okay. And if I go and open up my serial monitor, since I have active communication, you could see all the debug information. So this here was actually the address 7. Okay, let me get out of that. And I could show you that real quick here by skimming down to 7 right here. So this is the status register. And by the way, this actually tells you that anytime you write to it, the first thing you get back is always going to be the status register. So actually, if I go down here, I'll just show you this once real quick here. So when I did this set payload here, if I actually looked at what data in 0 was, it would be the status register. You always get that whenever you start communicating with it, because when you're first writing the byte, it doesn't know what you're doing, so it just spits out the status. Okay? All right, so let's just keep moving through this. Okay, get the address. So spit that out. Let's jump down there real quick and show you that. It's a massive piece of code here. So like I said, you're sending down two things. You're sending down the address and whether or not you want to print. I have a little explanation there of what that means. So here, what we do is we do we pull the chip select low. We do a transfer of the address, because now when you just want to read a register, what you do, and you come down to the datasheet here. When you just want to read something, you go here to our register. Now it's just all zeros, so it's just the address. So you read the address, and then data 1 here will be what is in that register. Okay, and then you pull the chip select back high. And then if your info was a 1, basically goes through and prints out all of the stuff that's in the register. So it'll take all those 1s and 0s and make sense out of it. Okay? So you can see I have all these conditions here that make it really easy and prints out things. So if it sees 1s or 0s, it'll actually print out what's actually going on the chip, so you don't have to figure that out. So it helps with debugging this whole thing. Okay, let's get back here. Okay, so now oh boy. Okay, now we have another subroutine here. NRF write the bit right. I don't know why I wrote it like that, but basically what this does here is it'll write a single bit of any register in the chip. So the first variable you send down is the address. The second is which bit in that register. And then the lastly is what you want to write. Do you want to write a 1 or a 0 to that location? And this is important to do because let's jump down and take a peek at what that guy's doing here. Okay. Right here. Okay, so what this is doing is it'll actually first pull out that register. So it pulls it out, and now that register is in data in 0, or sorry, data in 1 here. And then if you wanted to write a 1 to it, basically what it'll do is do a bit set of that register just pulled out of bit add, so that's right here, of the bit address. So it bit sets or bit clears it, and then it'll actually write it back in. So you can see now we have the 32 plus the address, so now it's going to write to that register, and it writes in the modified register. So it's good because if other things are moving in that register, you don't want to affect those other things. You only want to write the single bit that you want to change. Okay, so hopefully that makes sense. And you can see here I'm writing all kinds of things. So the first thing I'm doing here is putting it in RX mode. So let me show you that real quick. I'll pull up in the data sheet here. So you can see first thing I'm doing is I'm setting this bit to 1, throwing it in RX mode. Then I think what I'm doing next here, I'll take a look here, is I'm putting it in power up mode. So then I'm writing this bit here to a 1. So now it's powered up. It's in RX mode, it's powered up. And then the next two things I write to are to set up the interrupts. So like I said, I only want to call an interrupt when new data is ready. So the only interrupt I really care about here is this mask RxDR. So to clear these two guys or make them not do anything, this TX and max RT is I just write a 1 to them, and you can sort of see here in the datasheet, interrupt not reflected on the IRQ pin. So that's why I wrote a 1 to those two guys, and that's exactly what I did here. Okay. Up next is I flush out the RX and the TX FIFO, the first in, first out buffers. And if you go up here, you'll see where that is given right here. Flush TX, flush RX. So I'm basically just pulling the chip select line and shooting that out the pipe to the device. So flush your RX, flush your TX, you know, just in case there's anything, any garbage data that's still sitting in there, just dump all that out. Okay, then I call another subroutine here called clear interrupts. I'll jump down to that guy real quick here, show you what that does. Okay, so here we are, NRF clear interrupts. And basically all this does is it gets the address, the status, it grabs the status register. So I'll show you that real quick. It grabs the status register, which is 7 right here, and it looks at these 3 interrupt flags. So it's status 0 is where you set up, or I'm sorry, in the config register, 0 is where you set up what you want these interrupts to be. Do you want them to be reflected on the RQ pin or not? And then in this here, in the status register, is telling you, this is telling you whether or not they're active. So if the flag has been set. And the only way to clear these is to actually write a 1 to clear the flag. Okay, so basically what I'm doing here is grabbing the register, the status register, and if it's reads in as a 1, go ahead and clear it by writing a 1 to it. And I'm doing that for the RT, the TX, and the RX interrupt down there. Okay. All right, now we're getting into the good stuff. Finally, what we do is attach the interrupt we attach an interrupt to the interrupt 0, which is digital pin 2. The IRQ pin is connected to digital pin 2 of the Arduino to call get data, which is a subroutine, on the falling edge of that pin. So this pin will go low when new data arrives on the transceiver. Okay? Now what we do is get into the good stuff. So this is how we actually control the other Arduino. So look here, check this out. I'm doing an NRF pin mode, and the way I set this up is digital pin 3 and then I send a 0, meaning I want it to be an input. Okay, so digital pin 3, use a 0 to claim it as an input. And then I can do a write of that pin by NRF pin write of digital pin 3 and make it a 1 to drive it high. And what this will do is enable the internal pull-up of that pin. Okay, so I think now we're ready to talk about how these are all set up here. So I'm going to go through some of these now and show you some of the things you can do in the code. But I think just before that, I'm going to set something up here in the loop. Where's it at? Here's the loop is right here. So now I'm just going to show you at a high level what's going on here. So if you look at the code that's not commented out here, you can see that if NRF pin read of 3 is equal to 0, then go ahead and make digital pin 7 high, then low, high, low, high, low. This is the code I just demonstrated for you, which is this is being ran on the host microcontroller. So you can see when I do an NRF pin read, this is not a pin read of the local microcontroller. This is actually reading the pin of the second microcontroller. So it's kind of cool. And if I did, I'm trying to see what I have set up here. Yeah, if I'm ready to. Okay. And then if I go, I'm actually going to try to. Okay. I just wanted to try something there. So there's another thing you can do here in this code, and that is a ping, which is very useful for debugging, and I think that's where I want to start the explanation here of how this all works is by a simple ping. So I'm actually just going to make sure I got the right one. I'm actually just going to do a ping here. Upload that to the host Arduino here. Okay, and it should be done here. It's done. Open this up. Okay, so basically it sets up and then it's just telling you if the ping was successful, if it was a fail. And yeah, there are a few fails. It's not perfect communication, but that's why you send multiple bytes to the thing. You keep sending your data until you get a successful read back. And I'll show you what I mean by that in a second. Okay, so let's just explain this ping thing for a second. We'll talk about pin mode and pin write. But the most basic thing here is just by sending something over to the Arduino and then getting it back. Okay, so here is that subroutine to ping it. And basically what we're doing is grabbing a random byte, so something from 0 to 255, and then we do a transmit here of ping, and it starts with 6, and that's a code. So on the receiver side, when it sees a 6, it knows it's getting pinged. And when it gets pinged, it knows to send it back with another code. And when we get it back, we see that code, and then we see what we pinged with, and then we match those up to see if we had a successful ping. And we'll explain that in a second. So basically what it does here is it transmits, waits a little, and then if the data 2, which is the data that's coming back, is equal to my ping, then I know I had a successful ping. So now let me show you this transmit. So this is how to actually send data out. Okay, we'll go up here to transmit. And it's right here. Okay, when you transmit, you need 3 bytes going in. Right now, they don't really mean anything. I have them labeled as mode, pin, and value, but they really don't mean anything yet. Okay, the first thing I do is I flush out the TX. So if there's anything already in there, just get rid of it because I'm about to send new data. Then we pull the chip select low. We do a load TX payload, which is, if I go right up here to this command, right up here. So load the TX payload right here. So this is where you could load up all your 32 bytes, but in my case, I'm only loading up 3 bytes. Load it up. So first we tell it we're gonna load up, then we follow by our 3 bytes. Pull the chip select pin high. All right, now it's time to go into TX mode. And what it does is it pulls the chip enable pin low. Add a little bit of a delay in there. Then we do a bit write of the configuration register 0, bit 0, and write a 0 in there. Now it's in TX mode. Put a little another slight delay in there. Make sure everything was written. And then we write the chip enable pin high. And this is where this critical delay is at. And I experimented with different values of this delay. And what I'm talking about here is the delay now from when this chip enable pin has gone high until you have written back to the configuration register A1 to put it back into RX mode. So I've experimented with different values here, and if it's too long or too short, it doesn't work. So I found the sweet spot right now is just with a delay of 1 millisecond. And that seems to work pretty good. So you put it now back into RX mode, and at this point right here is when the data is flying out of the transceiver back to the host receiver there. Okay? And then that's it. We're done with the transmit. Then what we do is we just hang out here. So if you go back here to the ping, you'll see that we do a transmit and then we wait 15 milliseconds. Now during this 15 milliseconds, the data should have arrived on the other end, and it should have caught that data and then sent it back. So now let me show you what that looks like over here. So if I go now to get data, so what should be happening here is we send the data out, it gets caught by the other end, and on the other end, this subroutine is called immediately because the IRQ pin goes low as soon as data is in the transceiver. Okay, new data. So what we do is we simply do, we pull the chip select pin low, and then we do a command to read the payload. So you go back over here and you'll see read the RX payload, and then followed by 3 bytes. And this is the actual information that's coming in, the 3 bytes here, data in 1, 2, and 3. Okay, so now we got the data. That's all there is to it to get the data out. Well, there's a little bit more to it, and I'll show you that in a second. But as soon as we get the data, then we start figuring out what the data is. And there's all these codes in the data. So the first byte that I send is what to tell the transceiver what to do. So I just showed you that we sent a 6. So when it sees a 6, now it saw 6, and what it does immediately is it just transmit back. Actually, there should be a little bit of a delay. Actually, in this it doesn't matter. But in here, you'd want to have a little bit of a delay before you transmit, because if the other guy just sent his data, it's caught immediately, and you send data back, it might still be in the transmit routine. So anyway, you might want to add a little delay in there. But what it does here is it catches the ping, and it immediately transmits back, but this time starting with a code of 3. And it transmits the data it just saw, so 2 and then 3. So these are the 2 pings it got, so it gets that back. So then on the side that's actually sending the data out, this would be called again, and then you could see here that data in, if it's equal to 3, which is the echo back, data 2 here is equal to the data in, and data 3 is equal to that data in. And then that's what you see down there that we're comparing to. So if data 2 is equal to my ping back, we have a successful ping. So you could see, though, we're seeing a lot of fails in there. And I just noticed, though, that there is no delay in here, and I really think there should be. So I might actually give that a try real quick. I just noticed that right now in my code. So I'm going to upload that real quick. And basically, that's how a ping is used. Now, a pin mode, a digital write, a digital read are all with other codes. So if I sent something with a 1 starting out, that means I'm going to set up the pin mode of that Arduino. So followed by data 2, which is the pin I want, and followed by data 3, which is the actual mode of the pin. So if it's a 0, I want that pin to be an input. If it's a 1, I want that pin to be an output. And then we have the delay in there here. And then what we do is echo back that with a transmit of 3. So then we echo back that data, which would be then the pin and the mode right back. If it's a 2 being sent, that means that I'm doing a digital write. And if you read through all this, I think all of my comments will make sense. But if I send out a 2, that means that I'm trying to write to a pin. So data 3 is actually what the value I want to write, whether it be a low or high, and data 2 is the actual pin. And again, I echo that back with a transmit of 3. Okay, so that's pretty much it on the things I have right now. I also have 5, which will probably be for analog reads. Right now, everything is digital read and writes. But eventually, I do want to do analog reads as well, amongst other dedicated functions. Like if I had a temperature sensor on each board, 7 might be read the temperature, something like that. So while we're in here and get data, if I don't see a mode here, anything 1 through 7 right now, what I have, that means that no mode byte has been identified, and then just spit out the data that you did receive. So like if you just wanted to send like text or something like that, maybe you'd actually start that with like a 7, and then the following bytes would actually be the text. So if you just wanted to send messages or something like that, that's how you would do it. So anyway, that's how I parse all the data out. Then the last thing I do here is flush the RX FIFO. And then the most important thing that I think a lot of people screw up with is that that IRQ pin went low to call this subroutine, and the interrupt was flagged in the transceiver, so you actually need to go and clear that interrupt. And that's exactly what I'm doing here. In the status register, bit 6, write a 1 to it, and we'll clear the interrupt, and now that IRQ pin will go back to being high. Okay, so that's pretty much all there is to it. Now, if we get into it, you can see that, all these other functions are pretty much all copies from each other. So like pin mode here would be, the pin and then the mode, whether you want it to be an input or an output. And then what I do here, I'll just explain one of these, is I basically give it 10 tries to set the pin up. So what I do is I do a transmit of code 1, the pin and then the mode. I give it 15 milliseconds, and then I check the data that came back. So if the data 2 is equal to the pin I sent out and the mode is equal to the mode I sent out, then make I equal to 10, which would force me out of the for loop completely, and you're done. You can move on. If not, repeat that and keep going until you do get this. If you get all the way to the end, you'll get an I equal to 9. That means you got to the end, no pin was set, and then that would be a fail to set the mode. And then reset your two compare variables there, okay? Same thing with pin write, same exact thing. For pin read, it's a little different because pin read is actually not a void subroutine. It actually returns the value of the pin read you're trying to do. So like, it works just like a digital read of a pin in the Arduino language. So again, you're giving it 10 tries, and if the data 2 is equal to the pin that you sent out that you want to read, then get out and return data 3, which is actually the read that the Arduino on the other side read. Okay, and that's pretty much it. That's all the code here. I mean, it's really simple stuff. Let me show you maybe an example of this here. I'll get rid of the ping stuff and I'll upload that. Oh, actually, I said I was going to test out adding the delay. Oh, look at that. I added the delay, and you can see that the code is much better. And you can see that there's fails in here, and there's the reason, and I just wanted to make one more comment here, is that the reason, you know, that I'm trying 10 times to do this is that there's a trade-off between how fast you want to write and the quality of your data. So if I added more delays in there and did more double checking of everything and made sure that everything lined up, then I wouldn't have to do this. But that would all take time. But as you can see from this, that most of the time you're going to get it the first try. So in here, if you get it the first try and you get your data back and it was correct, then you might as well just use this method, because chances are it would get it the first try. If not, it would get it on the second try. And that's kind of the reason why I made my code so simple and didn't do all that checking. Now, obviously, you could go completely ballistic with all your checking. And if you go through all these registers in here, you can see all the crazy stuff you can do. And like I said too before, this is just my first draft of this protocol. Eventually, I want to get into, you know, talking to multiple sensors. So giving each sensor node an address, you know, and have them all talk to each other and talk back to the host. Or if one of them is out of range, but it can talk to another sensor node, it would pass its information along. You know, things like that. I also want to get into some of these low power modes and how do you put the thing to sleep and how do you wake it up, things like that. So you can go through all these registers and see that there's a lot of stuff you can do. So anyway, I hope that wasn't too long of a video, but you know, like I said too before, you don't have to use my code. You could use a library that somebody's already written and probably done a much better job with, but the way I like to do things is to break it down and try to figure everything out just using the datasheet. So anyhow, that is how to work with the NRF24L01. Thanks for watching.